Today I'm talking about Laconic deep learning inference acceleration. So this is a paper which presents a CNN accelerator, and the other part of this paper basically talks about how there's a lot of bit sparsity. So the first part basically talks about how bit sparsity is abundant um, in convolutional neural networks, and then it proposes to leverage that bit sparsity to propose their own hardware accelerator for CNNs. So let me just start by kind of talking about deep learning accelerators in general. So that's kind of what they go about in the introduction. Is at the end of the day, any kind of deep learning accelerator is just two things. One is data transfers, and that basically is getting your weights and activations to and from um, your memory, and the other aspect is your MAC or multiply accumulate operations, right? And so that's what they talk about in the introduction, and then they basically talk about how there are at least four categories of of hardware which kind of improves energy efficiency. That's what they talk about in this paper, and one of the things they kind of highlight is that their Laconic deep learning accelerator is kind of energy efficient for inference, right? And so this is so they basically go through all the four different kinds of categories of those kind of accelerators. One is it tries to kind of fuse computations on multiple levels. So basically, kind of fusing together different operations in the process. And the other thing they talk about, the second class that they talk about, is quantization, and how you could basically um, layer wise, or selectively, kind of on specific layers, kind of prune um, your prune your weights and your accumulate sorry prune your weights and your activations, um, and so that's what they talk about here. And the other the third class is where what they kind of propose lies in is bit sparsity and sparsity in general. So they talk about how there are a lot of ineffectual computation which goes on, especially when you consider that a big part of and that's what they propose as like more than 90% for 8-bit and 16-bit models, after you use both encoding, is basically zeros, right? And so whether or not you process those zeros, your accuracy or your output kind of remains the same, right? And so they talk about that. They talk about this as an approach, the bit sparsity as an approach towards achieving what they talk about in the Laconic deep learning accelerator, is that they leverage this bit sparsity into, and then basically they decompose your multiplication into kind of simpler ones, and like accumulations and a bit level. And they kind of instead of so they say that basically it's counterproductive to talk about words, bits instead of word, because you can actually parallelize those word-wise multiplication accumulations faster, right? But they talk about, because there's bit-level parallelism which can be leveraged for this process. That's what something that we'll discuss and they talk about in the paper. We can basically so that's what their contribution is twofold. So for the first thing to talk about is they kind of prove or motivate that, because there's a high amount of bit sparsity in convolutional neural networks, they basically motivate to leverage that into their hardware design, right? And the other thing is they do obviously propose the hardware accelerator, the Laconic accelerator, and they discuss the architecture for Laconic, and then they go into specific um, specific kind of decisions they made into making that accelerator. So that's your introduction here. Section 2 is talking about bit sparsity and how that's abundant in convolutional neural network, and they use that to motivate their approach towards like a bit level parallelism, and kind of leveraging that sparsity, and reducing or eliminating ineffectual multiplication, or multiplication which involves zeros, to speed up the MAC, or the multiplication and accumulate process, right? Um, so this is what it is. So they talk about how, if you imagine like a convolutional neural network with C, H, and W channel height and weight respectively, and you have F maps and O maps as the filter maps, and the outputs to those filter maps, and this is what your output kind of looks like, right? So this, they talk about how an output, this is the formula for the output element NYX after convolution, right? So W is your weight, A is your activation, and O is your output, right? And this is just the formula for convolution, right? Section basically talks about how the different approaches towards exploiting this sparsity, and so they mentioned that there are works, previous works, which only maybe leverages activation sparsity, and then there are papers which talk about activation and weight sparsity, right? And then what they propose is bit sparsity, right? So this is where they take the activation and the weight terms, and they use both encoding and base leverage the bit sparsity in the both the activations and the weights, right? And so that's what their work here is, right? So Laconic uses both. The T here basically represents bit sparsity, right? So T is the element, or the bit element, for those specific kind of activation and weights. So A is your only using your activation sparsity. A plus W is your activation and weight sparsity, and so on and so forth, right? So they basically say that, their novelty here is they use both activation and weight sparsity, and both encoding to get those bit level bit level terms, and leverage that, and so that's what they're talking about here. And so this section talks about the Laconic processing element, and and its architecture, and the histogram based approach it takes. And so this is the figure which flattens out or lays down the Laconic processing element and its different stages. So starting off, we basically have 16 um, 3-bit weight terms and their corresponding sign bits. And the first stage is basically taking the term pair products, and so basically each of the term are multiplied, leveraging the fact that all terms represent powers of 2, right? And so the exponent weights are basically obtained by adding the exponents and of the weights and the activation terms, right? And the sign is basically calculated using a XOR gate. And step 2 is decoder conversion, right? And so here we're basically doing a one hot encoding for the 4-bit exponent result which we get here. And then the next step is the histogram accumulation, right? And so the idea here is uh, it generates a histogram accumulating these 16 one hot encoded numbers and into 16 buckets, corresponding to powers of 2 to the power 0 to 2 to the power 15. And so each bucket basically contains the count of inputs corresponding to each of the buckets, each of the power values of 2, right? And it takes 6 bits to accumulate the range of the sums here. So that's what the output here is, right? And this next step is basically grouping and concatenation. They also call it alignment. And basically, instead of reducing the 16 count directly, which would be inefficient according to them, uh, it basically optimizes the process by grouping and concatenating counts, right? And the idea here is, this is the idea which is this is based on, actually, is to talk about in a lot of detail here, is basically, you can do it because there are no overlapping bits that are one among those groups, right? And so you're not really losing information here. So this is what step 4 is. Step 5 is basically an adder, and added tree reduction, to be exact. And the idea is that the concatenated values from the previous steps are added, um, using a 6 input adder tree, and the output is a 22-bit partial sum here, right? And then finally, this is your accumulation stage. So the partial sums are accumulated here. Um, and so this is basically your whole Laconic processing element architecture. Um, Coming to what we were discussing previously in step 4, shrinking the adder tree. This is your next section. Shrinking the adder tree, right? So here they expand upon what they meant in step 4, where they talked about stage 4 and 5, right? And so they kind of explain that, since um, each of the inputs, the 6-bit inputs in this case, um, don't have any overlapping ones. So because the sixth input here, like what they explain here, is the sixth input uh, would be shifted by 6 bits here, and so it'll be, succeeded by zeros. So you can pretty much concatenate these two inputs, and so instead of having a alignment and a summation step, it can pretty much be replaced by this concatenation unit. That's what they explain here, and this is obviously, recursive, because and it it'll have like 6 group of inputs where I mod 6 is equal to 0, and so this is what they show here. And going forward, they talk about lowering the area of histograms, right? So so initially these buckets are designed to accept 16 2-bit inputs, and each of them, kind of represents 3 possible values: +1, -1, and 0. And this setup means that basically every bucket is connected to all the decoders and matching the output corresponding to the specific values of 2, power of 2. And so the optimization strategy which they propose here is to redesign these buckets in a way that it can handle only 8 inputs instead of 16. And so that way, the amount of area that's required is significantly lesser, right? And to achieve this, processing they want to basically we want to be processing multiple amounts of data at the same time. And so so they again talk about how, since the decoders are one hot, and only the output, that means, like, only one bit is set to 1 and another is set to 0, so they won't overlap, right? So you can pretty much kind of encode them by kind of overlapping them, right? And so that's what they talk about here. And so now let's get to tile organization. They take this example of this kind of a tile organization where they have 8 cross 4 of a grid of 32 LPEs, and they kind of explain the organization here. And so basically, multiple LPEs can be grouped together in various configurations, and which they call a tile, right? And so this is supported by two input scratch pads for the activation and the weights, and there's the third for storing the outputs here, and they're connected together. Um, and the idea is that they want to enable data reuse and minimize the required number of connection feeding uh, for feeding data into the LPs, right? And so that's what basically they talk about in this section, and they kind of motivate that going forward. That these kind of they motivate the reason for data reuse and minimizing the number of connections. So that's where what we'll talk about in the next sections of tile synchronization. They talk about the synchronization technique called comb synchronization, and the motivation behind it is when you basically when all the concurrently passed A and W pairs um, when, or the next basically group of A and W pairs are started processing only after the first group completes, and that's obviously a disadvantage, and so and that also gives us some scope for speed up, and so that's where they they need to basically figure out a way to parallelize it even more, and basically that requires then some synchronization techniques. So they talk about um, uh, passing those in 16 independent groups, and so the synchronization groups contain, in this case, A0, A16, A24, A40 to A48, and the second group contains A1, A17, and so forth. And so it kind of forms like a comb-like pattern and kind of goes through the entire grid of your data, and so that's why it's called comb synchronization. And so then we'll go on to data type composability. So in this section, they basically motivate that there's some neural networks like YOLO. They require 16-bit precision for certain layers, whereas for most of the layers they require only 8-bit precision. And this variability in precision kind of poses a challenge in the elements designed to operate with a fixed data width. And so the way Laconic tackles this challenge is basically by supporting data type composition that are both spatially and temporally, and that allows like a flexible um, adaptation to the precision requirements of different layers, right? And more specifically, in case of spatial composition, um, it involves using multiple 8-bit Laconic processing elements (LPEs) in tandem to perform 16-bit computations. And so essentially, it combines output of several LPs and achieves that higher precision without modifying individual LPs. And this is useful only when like a subset of layers that require high precision. So it still remains efficient even when handling the 16-bit computations. The other is the temporal composition, where um, the it modifies the operation of an LP to handle both 8-bit and 16-bit operations, and though it introduces additional complexity, and it requires more cycles for 16-bit values, and this method allows like even a single LP to adapt its processing capabilities, and it basically means that it's versatile enough to also temporally kind of compose and handle higher bit computations. And so the authors argue, based upon which to use. They say that they both have their advantages and disadvantages. and based upon the requirements of the neural network and the how prevalent those high precision values are, temporal composition basically offers higher throughput per LP for a network of sporadic. If there's a network where with there's sporadic 16-bit requirements, and so it requires larger LPs though, because and more control, because it requires more complex control mechanisms. Spatial composition, on the other hand, is simpler, but it requires a lot more LPs for processing the layers with 16-bit data. So that increases the area. And implementation for both 16-bit and 8-bit computation. So they basically go into this in this section. Um, and so in that, Laconic can basically split the processing of 16-bit across multiple LPs or cycles. Like we just discussed, it can divide 16-bit activation into upper and lower bytes, and processing each part with separate LPs or different cycles. And again, so this uh, allows the LPs to handle mixed precision requirements efficiently. So this is pretty much what this section kind of talks about, and we'll go on to the next section in a bit. Spatiotemporal term processing. Um, so the idea is that the paper basically extends the capability of Laconic architecture from just intervalue bit level parallelism to also intravalue bit level parallelism. And what this means is that instead of processing all the bits of a value sequentially, it can handle parts of the same value parallelly or spatially. And this method allows multiple bits of a single value to be processed within a cycle. And to implement this, they made some modifications to the input handling and the booth encoder, while kind of keeping the Laconic architecture. Specifically, they assign two input lanes per weight, adapting the booth encoder to both the outputs up to the two terms per cycle. The architecture basically then exploits bit level parallelism within values. So they don't have a diagram here basically explaining it, but I think the rest of the architecture remains the same. And so then they discuss the benefits here. Um, so they talk about reduced synchronization overheads, and this basically means that overall it reduces the need for synchronization across the network, and it streamlines the processing. And then it talks about improved utilization for sparse layers, and this basically means that uh, underutilization in layers with minimal data reuse. And so they talk about how fully connected layers have minimal to no data reuse. And the third advantage, which they cite, is flexibility for various layer types. And the idea here is that this method provides an advantage for configurations with fewer filters than processing rows and optimizing hardware use. So, so this is pretty much this section, and then we basically get to memory system section. They introduce the idea of second level memories, and that's specifically designed for activation and waits. Um, this separation is crucial, I think, which the author mentioned, is because in most neural network models, storage and traffic requirements for weights are significantly higher than those for activations. And to address this, they are basically um, uh, they talk about two memories: the activation memory (AM) and wait memory (WM). Um, and the activation memory is basically capable of holding input and output activations for any one layer at a time. And in case of the wait memory, it's designed to fit concurrent set of filters uh, for each layer, and that's that's basically how they kind of define the two memories. And um, coming to optimization, so for computational imaging models, which are fully convolutional, and so they decide a few different kinds of models here. In those cases, the system adapts by ensuring that the activation memory can accommodate a full row of input and output windows for any layer, and the WM or the um, weight the weight memory is sized to fit all the layers, and so that basically optimizes the specific demands for specific models. And then they talk about this DPR lossless compression, and this is basically to minimize the off-chip traffic, and the author basically explain is a major concern for energy efficient hardware accelerators. And the architecture employs DPR lossless compression, and this technique is based on the observation that most values in the neural networks are small, and only with a few kind of high magnitude values. Then the values are basically encoded in groups, and with the encodings with tailored to maximize the value in each group, and that basically significantly reduces the memory footprint. Um, so that's what basically they talk about here, and then they talk about access patterns and reducing the off-chip traffic. And um, so this is basically this section on memory system. Apart from that, this paper basically does a few evaluations and comparisons with this other bit parallel accelerator done now, and they also compare results with Iris. Um, but I think that's pretty much in terms of the architecture and the whole flow of the Laconic hardware accelerator. So that pretty much sums up this paper, and